We'll be looking at question 18, June 2019 paper. This is a question on transition metal ions, complexes, and a bit of redox as well. So let's have a look. This question is about reactions of ions and compounds of transition elements. Oh, what's happened there? Where's that gone small? Okay, let's try that. Okay, a student carries out 2 experiments on solution containing chromium 3+ ions. So you've got the complex here. Over here, student adds an excess of aqueous ammonia to a solution containing chromium 3+ ions until a purple solution is formed. The student carries out the following reaction sequence. Let's have a look. Sodium hydroxide is added slowly to a solution and a gray-green precipitate forms. Then an excess of sodium hydroxide is added and the precipitate dissolves and a green solution forms containing a 6 complex ion. So let's have a look. It goes on further. Hydrogen peroxide is added to the mixture and the boiling tube is heated. A yellow solution forms. This is something that I don't think I'm fully aware of, this reaction. Let's have a look. The solution is then, in the boiling tube, is acidified and the solution now contains dichromate ions. We've met dichromate ions before in the oxidation of alcohols. But step 3, I'm a little bit unsure. Let's look deeper into that. What is the formula of complex ion in the purple solution that forms in experiment 1? You see, when you're adding excess aqueous ammonia, let's have a look at the color chart. Excess ammonia to a chromium 3+ Cr3+. That's a typo there. That should read as a 3 there. 3+, not 2+ there. Cr3+. Yeah, it turns excess, it gives you a purple color solution. Purple color solution. What is the formula of the complex ion in the purple color solution? So all the water molecules have been substituted with ammonia. So you've got 6 of those, and the charge still 3+. Okay, suggest an equation for experiment 2, step 1. You see, what you're doing here, include state symbols, it says, include state symbols. So you've got chromium 3+ ions. These are in the aqueous state. These react with hydroxide ions, again, which are in the aqueous state. And it goes on to form chromium 3 hydroxide, which is in the solid state. And to balance, put a big 3 there. You must ensure that you get these state symbols in. Aqueous to give you a solid. Very important. Next question. Draw a 3D diagram for the shape of the molecule that forms in experiment 2, step 2. So in here, it tells us that it forms a 6-coordinate complex ion, 6 bonds, so it'll be octahedral, and you're adding excess sodium hydroxide. Excess sodium hydroxide, and the precipitate dissolves. You see, going back to that chart, when you're adding, this is chromium, Wait a minute. Yeah, what we got here? Yep, chromium. Wait a minute. Where's chromium? Chromium hydroxide. Yeah, got chromium hydroxide here, which is a dark green precipitate here, in the addition of sodium hydroxide or dropwise ammonia. Excess sodium hydroxide, and it gives you a dark green solution. Again, we want to learn all these colors, precipitates and solutions. Very important. So what this gives you, you've got your chromium in the middle. Let's draw our 6 bonds. Let's draw our 6 bonds. This diagram is very important. You want to practice drawing it. If you've been following these videos, you'll see that we've drawn this many, many times. There's very valuable, precious marks. Make sure each coordinate bond is to the oxygen, and then you put in the H afterwards. It's all about connections. You will lose marks if the connections are not there. It's the lone pair of electrons on the oxygen that forms the coordinate bond. You see chromium is 3+, and you've got 6 hydroxide ions. So the overall charge is going to be 3-. What is the formula of the ion that causes the yellow color in experiment 2, step 3? You see it's saying hydrogen peroxide is added to the mixture. This mixture is the chromium complex, and hydrogen peroxide is added. I think I've ever seen it being tested like this before. So I went to the book, which is this is written actually by the examiners. I think there's a bit of a lag on my connection. What's going on here? Yep. This is from the, what's the author's name? Rob Ritchie and Dave Gent, Oxford publication. And here, lo and behold, you've got oxidation of Cr3+ ions to Cr or chromium chromate 6 ions. Chromate 6 ions. Just highlight that. So we need to be aware of this. And this color, does it give you a color here? Because it can form oxidized in oxidized. Okay, it's not giving us the yellow color anyway here. Yeah, it hasn't given us the color, but it gives us the conditions. Hot alkaline hydrogen peroxide with Cr3. And when in doubt, look at the specification and look at the textbook. I've not seen this question asked, hardly. So let's carry on with the questions. What is the formula of the ion? So the formula of the ion is the chromate, Cr, chromate 6 ion. And it's got a 2- charge. You see each chromium is +3, oxygen is -2. Sorry, chromium is +6, sorry. And that gives you the overall 2- charge. This is called a chromate. Chrome as in chromium, and 8 as in oxygen, and 6 as in the oxidation number of the chromium. State the color of the solution that forms in experiment 2, step 4. Experiment 2, step 4, which is here, acidified dichromate is an orange color. We learned that in year 1, in oxidation of alcohols. So this is orange. Okay, moving on. Vanadium ions have 4 common oxidation states. Table 18.1 shows the colors of these ions in aqueous solution. We do not need to know these colors off by heart, the vanadium ones, and they've been given to us in the question. Now, complete the electron configuration of a vanadium 3+ ion. Vanadium has 23 electrons. So let's write this down. 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. That's the vanadium atom. Now, for the vanadium 3+ ions, we need to remove 3 electrons. So 1, 2, and the third one will be from here. So it'll be 3d2. Yep, and the mark scheme supports that. Now, let's have a look at this. To make it a bit more easy on the eyes, I pre-color coded this just to help us understand it. The student, it says in question B part 2, the student adds excess iron to a solution containing VO2+ ions and observes the color of the solution changes from blue to green and then to violet. So really, what's happening, we're going from VO2 ions that form V3+ ions, and those V3+ ions are further converted into V2+ ions. Why is that? Let's have a look at our redox systems and the electrode potentials. You see, we've got, let's look at iron, excess iron. Let's highlight that here. Iron is excess iron is added to a solution VO2+ ions. VO2+ ions. Now, there's 2 VO2+ ions. There's here and there's here. But the thing is, we want to form V3+ ions. So I think we're going to use redox system 4. Yep. And yeah, so we've got these two. Now, the thing is, redox system 4 is more positive, the electrode potential. So that's going to gain electrons. It's going to go in this direction. Iron is the electrode potential is more negative. The more negative the electrode potential, it loses electrons. It's going to go in this direction. So what you're going to get, ladies and gentlemen, is we are going to form V3+ ions, and it forms Fe2+ ions. Now, V3+, as it shows in here, V3+ forms a green solution. So that explains why it's green. And then it goes to a violet. You see that V3+ is also over here in redox system 3. And you see this electrode potential is more positive than redox system 2. I'll just repeat that. Redox system 3 is more positive than redox system 2. So this will gain electrons, and the iron again will lose electrons. And so what you're going to do, we've got excess ions, so this then goes on to form V2+ ions. And V2+ ions are violet in color. That's worth 3 marks. How would you word that? Just what we just discussed and putting it into words. So we can start off with so we can say VO2+ goes to V3 plus, and V3 plus goes to V2 plus. Why does it do that? Why does it do that? Because redox system 4 is more positive than redox system 2. And what we can say is as a result, we also, the equilibriums, these equilibriums, we want to refer to them and say which direction do they shift in. So redox system 4 shifts to the right, and redox system 3 shifts, redox system, also shifts to the right. These are the main points. So this goes to the right here, forms V3 plus, and then V3 plus also shifts to the right to form V2 plus. It's asking construct an equation for the first color change from blue to green. You see, blue to green was where VO2 plus under acidic conditions is reacting with iron. And you see, iron produces 2 electrons, so we're going to need to double this up. Put a 2 there and put a 4 there. That goes on to give you Fe2 plus and some V3 plus. Remember, we're doubling that. And some water, 2H2O. So we're doubling it. Yep, and the mark scheme supports that. All we did, ladies and gentlemen, we combined redox system, let's get a different color pen, redox system 2 and redox system 4. And redox system 4, we multiplied it by 2 to balance these electrons, these one electron here with these 2 over here. And we got our overall equation. Okay. Moving on. What we got here? You got iron 2 gluconate. So you've got this strange, complex, complicated or complex ion here. Is an active ingredient in some brands of iron supplements. The student carries out an experiment to determine the mass of iron 2 gluconate in 1 tablet of iron supplement using the method below. Student crushes 2 tablets, dissolves the powder tablets in dilute sulfuric acid, giving the sulfuric acid. If you do this practical, it liberates the iron as Fe2 plus ions. The student makes up the solution from stage 1 into, this is the total volume. Out of that volume, this much is titrated manganate. And this is the volume was used. In the information, 1 mole of manganate ions react with 5 moles of iron 2 plus ions, 1:5 ratio. You've probably seen this equation many times. I'll just write it down here. Fe2 plus reacts with MnO4 minus under acidic conditions, which goes on to give you Mn2 plus 4H2O and some iron 3 plus. Put a 5 there and a 5 there. That's the overall redox reaction. It's a 5:1 ratio. Oops. It's asking, explain why the student uses this concentration for this type rather than the more usual concentration of this one used in manganate titrations. Why is the student using this one? I am thinking well, if we used, let's look, this is the titer that was used here, 13.5. If we use 10 times greater the concentration of this, that means the titer would only be 1.35 centimeters cubed. So if you had 1.35 centimeters cubed, the percentage error to get this reading would be much greater than 13.5. So it's about errors, ladies and gentlemen. And the idea that a large titer would give a smaller percentage error. Moving on. Use the student's results to determine the mass in milligrams of iron 2 gluconate in 1 tablet. Give your answer to 3 significant figures. You see, let's have a look. We've got here volume, convert this to decimeters cubed, multiplied by concentration. That gives you the moles of manganate in the titration. And we need to multiply it by 5 to give us the moles of iron in 25 centimeters cubed. But that 25 centimeters cubed is out of 250. So we need to times it by 10 to scale it up. Where does that 10 come from? It comes from this, that 25 out of 250. This gives us the moles of iron. And once you've got the moles of iron, what you do, you then multiply it by the molar mass of iron 2 gluconate. So that would be C12H22 FeO14. And that gives your answer in grams, but we want it in milligrams. So how do you convert grams into milligrams? You times it by 1,000. So let's work out the MR first. 12 times 12 plus 22 plus 55.8 plus 14 lots of 16. 445.8. 445.8. divided by 1,000, 002 times 5 times 10 times 4458 times 1,000. And you see the readings we got is for 2 tablets, but the question is after only 1 tablet. So we need to divide it by 2 at the end, which is a crucial step. And it wants it to 3 significant figures. We get 301 to 3 significant figures. Okay? And if you get 301, where's the 3 marks from? Volume times concentration. Actually, let's have a look carefully. Where those? Oh, 5. Oh my goodness. Volume times concentration multiplied by 5 is worth a mark. Multiplied by 10 is another mark. Multiplied by the molar mass is another mark. And dividing it by 2 and converting it to milligrams is another mark. Wonderful. This is the last part of the question, and I think that's the end of that question. Yes, it is. Iron supplements contain iron 2 sulfate or iron 2 fumarate. The information table 18.3 is taken from the labels of 2 iron supplements. Choose which iron supplement, A or B, would provide the greater mass of iron per tablet. How would we work this out? We would work it out. You've got the mass there. So 180 milligrams. Convert milligrams into grams. Divide by 1,000. So you got your mass of the iron compound, mass over MR, or relative formula mass, iron 2 sulfate. That will give you the moles of that iron compound. And we then times that by 55.8 just to get the iron on its own. And the other calculation is 210 over the relative formula mass of iron 2 fumarate, which is C4H2FeO4, and times that by 55.8. And let's see what that gives us. Oops, convert that to grams. And if we're comparing milligrams, we can convert it back into milligrams by timesing it by 1,000. (1.18 milligrams). Wait a minute, let me just work this out again. Oh, missed a step. So 6.1. To the other one. (69.0). So that's B and that's A. The answer would be B. B provides greater mass of iron. This was only worth 1 mark, but there's quite a bit of calculation to that. this is the end of this question. I will see you tomorrow.